Welcome to class. Good to see you. It's Wednesday, July 1st, and we're in the middle of chapter 18. This is part 3. Tomorrow is no class. It's part of, or Friday, sorry. Friday, July 3rd. It's part of the 4th of July weekend, so no class for that. But look, we've got test 1 here looming or coming up very quickly. Monday, July 6th, over chapters 16 through 18. It will be multiple choice, 40 multiple choice questions, similar to my multiple choice questions that you see on the sample test there. That's already on Learning Suite. We'll go over some of that here the second hour today. Let's see, tomorrow is quiz 3, which is right here, which includes a multi-step electrophilic aromatic substitution exercise. So you need to be into the homework problems for chapter 18 in order to do well on that quiz. But PDF again is on Learning Suite. Make sure you look at that, print it off, do it, and then upload your work by Thursday, July 2nd there. And also because we're finishing chapter 18 today, what does that mean? Homework 3 is also due tonight. So we've got a couple things due here before test 1. So we'll be reviewing for test 1 here the 4th hour coming up. Okay, so just to review and where we left off last time, we were doing electrophilic aromatic substitution on di-substituted or already substituted benzene. So we already have a functional group on there. Remember, we identified some electron donor groups, which by resonance, these can donate electron density of the lone pair. We'll look at the details of that here in a second. Alkyl also, we saw toluene last time as an activator. And when you add the second electrophile, it goes either ortho or what? Para. The deactivators are meta-directors. They deactivate all positions on the ring, but they deactivate the meta position to a lesser extent. The ammonium cation and the nitro group are the strongest deactivators. All these deactivators here, no Friedel-Crafts reactions can be done. The Friedel-Crafts electrophiles are the weakest electrophiles. Carbocations and those complexes with those Lewis acids to form the carbon-carbon bonds. Those do not occur if we have electron withdrawing groups. All right, here's some examples on the board here that we can go through, keeping those things in mind. And what do we have here? Phenol, and we have nitric acid, sulfuric acid. So what type of reaction are we going to do here? Right, nitration. All the reactions are one of the 5 key reactions, right? We have nitration, sulfonation, halogenation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. There's only 5, fortunately. The problem is now, with an existing functional group or functional groups, as we'll see, multi-step synthesis, we have to analyze whether it's going to go at the ortho or the para or meta positions. But what type of group is phenol? Right? It's an electron donating group because of the lone pairs here. So the products are right here, the ortho plus the para. And, you know, don't worry about the percentage of the two. You can always separate the two. Usually the para has a lower melting point. You can usually do a recrystallization and get the para pure from the ortho, but don't show any meta product, okay? And what about the speed of this reaction? It's very fast. So let's look at a little bit of the mechanism here. Remember the true electrophiles, the nitronium cation. So let's go ahead and pull the electrons out and form the intermediate. What's it going to look like? Well, we're going to have this, and the nitro group's going to be on there, hydrogen, and what else do we need there? Oh, we need a plus charge. And notice when we do the ortho pathway here, we have resonance here, here, and here for the plus charge. Remember we did that exercise last time, and we analyzed all 3 of those resonance contributors to the true overall structure of that intermediate. Anything that can stabilize This allyl-cation will speed up this reaction. Not only that, it'll control, of course, the selectivity. But what do you notice about this cation here? Well, it can benefit from this resonance overlap, right? And that's the key thing of phenol and aniline. You can get this extra resonance structure with the plus charge on the oxygen there. And then, second step here, we have the base. We use water to take off the proton and push the electrons back up, and that directly goes to the ortho. You can have a similar analysis here for the meta pathway for phenol, and you'll also have a resonance structure. Well, you have a plus charge right next to the oxygen, which is a good thing by resonance. So it's extra resonance effect. It's a resonance donor, okay? Notice we don't show any meta product. If we did the meta pathway, we'd have a plus charge here, here, and here. We'd never have the plus charge next to the oxygen. So that does not lead to a faster rate if you do the meta substitution with the phenol. Okay, let's see. How about the next one here? We've got aniline with bromine. And notice I'm leaving out the ferric bromide. Why? Well, this is such a strong activating group, this lone pair here. You can actually draw the mechanism now without even using the Lewis acid. So these are the two cases where you don't need the Lewis acid in order to get halogenation. All the other ones are not as activated, so yeah, you always need the ferric bromide, okay, or ferric chloride if you're doing chlorination. But we'll show this resonance structure here, leading to which product? So we'll have the cation on nitrogen directly if we follow that pathway there. And we got bromine and Br minus here. And how do we get to the product then? Well, we use bromide to deprotonate, push the electrons back, and look, which product do we get? We get, yeah, ortho. And it's the same thing for the para product. We should draw that for the aniline right here. Okay, so we can get a mixture of that if we do the monobromination. Now, one thing to notice about phenol and aniline with halogenation, either chlorine or bromine, we often get over halogenation at all of the ortho and para positions available. Why? That's because once you get one bromine on there, the halogens actually can, by resonance, donate electron density. And plus the halogen nation is activated because you regenerate the neutral aniline under these conditions, okay? So this is kind of a tricky thing. You often get the over-halogenation. But if we just show one equivalent here, we mean to show just the mono-halogenated product, okay? The ortho and the para from aniline. But if we have excess here, know that you can do over-halogenation. Now, one other thing on aniline we need to point out. If we do the reaction of aniline under acidic conditions and try to do a nitration, look what happens. It does nitrate, okay, but it gives not the ortho and the para product. Under these conditions, it actually gives the meta product. Why? What are the conditions now? Halogenation was neutral conditions. There was no strong acid there. But now for nitration, we have strong acid. So the first thing that occurs here is we put an extra proton on aniline, and this becomes an anilonium cation. Now, anilonium cation, what? Has a cation directly on the benzene ring, like the nitro group. This becomes what? A strong electron withdrawing group. And so what? It becomes a meta-director. When we put on the nitronium cation, we'll have a plus charge here, here, and here, and we'll never put the plus charge there if this is in that state. Now, if we want to get the neutral product here, we have to use some base, sodium hydroxide, something there. The pKa of the ammonium anilonium cation is about 5. So as long as we put enough base in there, we can get the neutral aniline back with the nitro group. But notice it's meta, okay? So that's another little caveat or extra idea there here in this chapter. If you use acidic conditions, the same thing for sulfonation with aniline. Now, it doesn't hold with phenol. Phenol is not as basic as aniline. Aniline can be easily protonated, especially with these strong acids. That becomes an anilonium cation, ammonium cation, and then it's a metadirector for nitration and sulfonation. Okay, let's see. What else have we got here? So a couple reactions there. Oh, we have benzaldehyde. Now, if you can remember from the chart or just looking at the structure, remember everything's related to structure here. If we have a resonance structure here, what? We have a partially positive carbon here, partially negative oxygen there. So what does this mean? With a plus charge here, this is a resonance withdrawing group, okay? By resonance. So this is pulling electron density out of the ring, and we don't want to put the plus charge here. So, well, where will the nitronium cation go here? Yeah, it will go at the meta position. So we'll get this product, okay? So it's a meta-directed group. And all of the carbonyls that are conjugated to the benzene ring and the cyano group, and of course the anilonium, and if you already have a nitro group on there, it's your exit to the meta position. Okay, let's summarize kind of these exceptions to the chart there, the little things you kind of have to keep track of, let's say. And I like to summarize these early on so we know that. In fact, I've already summarized the one there. Yeah, so if you've got the aromatic amine, the aniline here, and you're doing anything under acidic conditions, it will be the anilonium group, and it will be a meta director. Okay, you can still do reactions on it. Let's see, if you have the aromatic nitro group or any other electron withdrawing group, no Friedel-Crafts. So those are deactivated enough that those weaker electrophiles, the carbocation and the acylium ion for acylation, cannot occur. And so we'll just say no reaction. Now, there's an exception to the rule. If you have a strong donor and one of these strong withdrawing groups, you can still do Friedel-Crafts. So the book is a little too strict there. I'll show you the example of propofol. We'll show some examples of synthesis here where a strong donor can override the effect of a withdrawing group. But in general, make your synthetic plans and anything on quiz or test such that you avoid Friedel-Crafts with a strong electron withdrawing group. The aromatic halides, bromide and chloride, fluoride, iodide, whatever, these guys are deactivating, okay? They'll make their action slower, and that's why, because they're electronegative. And that's an effect through the sigma bond. Okay, so we said there were two factors, right? The inductive effect of being an electronegative group that can pull electron density out through the sigma bond. But they also have what? Lone pairs, which makes them resonance donors. And what? That leads to them being orthopara directors. But the reaction's slow. And they're slow because of the inductive effect through the sigma bond. But by resonance through the pi system, they can be donating enough. And so deactivating effect is a kinetic effect, but the resonance donation is the direction effect for the selectivity. So that's kind of the exceptions to the rule there. One other, maybe we should say, the aniline here for Friedel-Crafts is also no. And it's a little bit different argument. The Lewis acid then coordinates the lone pair on the ammonium group, forms a cation, and again, that slows it down enough that you can't do Friedel-Crafts directly on an aniline. I think that's all of the caveats there. I think so, yeah. Aaron's given me the heads up. I think we got them all there. So some of these kind of sneak up on you, and you'll be working the problems, and Maybe the solution manual will remind you of that. And they're kind of spread out in Chapter 18. I like to put them all in one place to remind you of these issues. But those are the ones you need to be aware of there. All right, let's see. So going on, let's up things here a little bit. And oh, I like to do this one. Speaking of overreactivity, so we've just done, di-substituted benzene. And we've shown you over halogenation, so we've kind of gotten into this a little bit. Let's take toluene and react it with nitric acid, sulfuric acid. So we're nitrating toluene. In fact, we did this one before last time, right? So it gives a mixture of two products. It can easily separate or use for multi-step. And it's what? The ortho and the para. Okay. Let me give you a little bit of results here on this. This is at room temperature, and it's done in 3 hours. Okay. If you stop it at that point, you can get a good yield of the di-substituted products. Like I said, you can separate these two easily by recrystallization, or if you need one or the other for multi-step, just carry it on that way. If we take this mixture here and treat it with more nitric acid, sulfuric acid, what are we going to do? Well, we're just going to put on another nitro group, a third functional group, right? But we have a deactivating group on here, and we have a donating group here. So are they in conflict, or can they reinforce each other? And what about the conditions here? Well, we need to up the temperature to 100 degrees in order to get this to go, because we have a deactivating group on here. I like to show some of the practical issues of these reactions. But if we do that, we can get a dinitro product. Okay. And we can kind of analyze this. Let's see, this is a meta-director, this is an ortho-para-director. We could have put the second one over here, but look, there's this open spot down here that's para to that and meta to that. They're actually reinforcing to give this product here, the dinitrotoluene. This one also, meta-director, right, ortho-director. So you're kind of seeing how multiple groups can work together here to get dinitrotoluene. Now we can even take this more with more acids, okay? And we have to increase the temperature to 160 degrees. And we need to be very, very careful about this last step. Why? Let's see, we're going to put on a third nitro group. Let's see, what is this? Let's see if we can come up with a name for this. What is it? Yeah, trinitrotoluene. Toluene is the parent there. And let's see, it's 2,4,6. Yeah, so it'd be 2,4,6. Trinitro. I won't draw it all out. Toluene. Okay, would be the full name. Have you ever heard of that reagent before? Hopefully you haven't used it too much. Unless you're a miner and doing road construction, things like that. Well, the 4th of July is coming up, so maybe this topic fits in there. What is this compound? There's an abbreviation for this. Let's try nitrotoluene. Yes, TNT. Explosive reagent. It is kinetically stable, but it's not thermodynamically stable. Some of these small organic compounds, when you get too many heteroatoms involved here, they can rearrange very quickly. And if you apply a shock here or an electric impulse or a spark or whatever, this compound very rapidly forms what? NO, NO2, CO, CO2. You've got a lot of oxygens and nitrogens on there. Let's see, what's the physical state of TNT? Yes, it's a solid material. It can be formulated into things like dynamite and other explosive materials. And then what? If the shock is applied to the system, it produces these 4 compounds, among others. There's some others here. Soot is also produced. Most of these, though, are what in the physical state? Yes, they're gases. So this is not combustion. This is detonation. This is another process where you rapidly go from a solid material that occupies a small volume in space to all of a sudden gas molecules at at these conditions generate a huge volume of space. So that's where you get the shock wave and the high energy effect of producing all those. And that is an exothermic process. Okay, so this is kinetically stable, but it's not thermodynamically stable. But luckily, it doesn't over-nitrate. At lower temperatures, you can easily get the stable non-detonation hazard compound. Anyway, we'll see some other explosive materials maybe later on in the course. But that points out the multi substitute benzenes that are available from this. Okay, let's see. How about this compound? This actually has a name. Xylene is the common name here. I don't expect you to know that. You could call it dimethylbenzene, that would be okay. But what am I showing here? I'm showing the meta-dimethylbenzene, or the meta-xylene as we call it. Okay, that's a great name, isn't it? It starts with an X, xylene. If you thought toluene was good, probably like xylene. All right, let's nitrate this and see what we get. And yeah, so we've got two groups on there. We need to analyze each one, their directing class. This is an ortho para director. This is also an ortho para director. And we have an ortho position in between the two, which might occur there. But which spot is more likely here? Sterically, this being in between two methyl groups is a little slower. Okay, you do get some of that, but there's one major product here that's formed. And this is an example where you have multiple groups that reinforce each other. You see, this one is an ortho relationship. This one's a para relationship. So that would be your major product. In fact, it's obtained in 85% yield. Don't show any product where that's meta to both. That would not benefit having the plus charge next to the two methyl groups. So this pathway here is highly stabilized relative to this pathway. So this one, you've got a reinforcing idea between the two groups. And that's probably the easier one. How about this one? Let's do para-nitrotoluene. And let's brominate. So we need ferric bromide in there. So analyzing this, we've got what, ortho here. And we've also got a nitro group as what? A meta director. So again, even though these are different types of groups, a donor group, withdrawing group, they are reinforcing each other, okay? So there's only one product here that's obtained in high yield, and that's this one, okay? Now we've got three different groups on there. We're getting highly functionalized benzenes. So you can see the power of these reactions and the different products that can come out there. But yeah, we have to look and see whether we're reinforcing each other or maybe in conflict with each other. Let's see. How about where we got a couple groups that are in conflict with each other? So how about paraxylene, okay, to use the term correctly here. And let's do Friedel-Crafts acylation, aluminum chloride. Now we got two groups, but again, this is ortho here. This is ortho here. But look, that's meta to that other one. But it's symmetric. It doesn't really matter. So if they're in conflict with each other, but there's symmetry within the molecule, all four of these spots are actually the same electronically. So that would be your major product where they're in conflict, but they give the same type of product. Okay, how about this one? We've got parachloro N-methyl aniline. So here's aniline with a methyl group on it, and here's a parachloride, okay? And let's do what reaction? Oh, bromination. One equivalent, and notice we have an aniline, so we don't need the Lewis acid. If you use the Lewis acid for halogenation with aniline, we won't take off points, but it's so fast without it. And again, like we drew that resonance structure. What do we got? And this is a strong, ortho para director. The para site is blocked. I like that when I finally get to this chapter and get to say that phrase, parasite. No, we're not in an insect class here, but The para position, yeah. And so this is what? This is also ortho director because of the lone pairs, even though it's deactivated. So that wants to go there. So here we're in conflict, right? Which one are we going to do? Are we going to go ortho to the aniline or ortho to the chloride? Which one do you think? There's a rule in the book, and if you've read that in detail, I think you can respond there. We're going to go with what? The stronger electron donor. And the stronger one, the higher up on that chart, right, is the aniline one. In fact, the chloride's deactivating, but it's still an ortho director. But because this is a stronger donor, we're going to go with that one. So the correct product here will be this, where we get the bromo there and the methyl aniline there, okay? So that would be our major product, okay? So some of these, you have to analyze them and see which side we're going to go on here. Okay, how about this one? Tert-butyl group and a nitro group. And we're going to give you these conditions. Ferric bromide, oh, we need 3 there, okay. So which are we going to go to? The alkyl group is an ortho para director, and the nitro is what? A meta director. So which are we going to go with? Well, the alkyl is a stronger donor, so we're going to go with that. And there's one other thing to point out here. The tert-butyl, because it's so big, it begins to block access to the ortho positions. You can get them into an ortho position to a tert-butyl. You have to heat things up, but look, you have an available para position, a parasite to the alkyl group, and that's opposite from the directing effect of the nitro. Why are we going with that one? Right, because the alkyl is a stronger donor. So our product will be this. Tert-butyl, nitro, and then bromo right there, okay? So we go with the stronger donor group. All right, now let's do these problems in a little bit different point of view. Let's take a starting material here, benzene. A lot of times our problems will start with benzene, but not always. Sometimes we'll put some other group on there, and you'll have to analyze, whether it's an electron donor by resonance or inductively withdrawing, whether it has the carbonyl directly next to the ring or not. Well, let's see. So how are we going to do some steps to get to this product? What are we going to call that? That's meta-bromo-acetophenone. How are we going to do that? So this is our product that we're trying to get to. So this is a multi-step synthesis problem. You provide the reagent, and importantly, the order of the reagents. Why? Because if you mix up the order, you might get different selectivity or maybe no reaction. If you try to do Friedel-Crafts on a strong electron withdrawing group, for example. So here we've got an aromatic ketone. We've got to do a Friedel-Crafts acylation of some kind, and we got to do a bromination. But what order do we do them in? Let's see. Analyzing this, what type of a directing group is a ketone, aromatic ketone? Right, it is a meta-director. So look, the bromide might come in second then. Okay, we'll have to analyze this. What type of a group is bromo? If we put that on first, bromo is an ortho para directing group. So what's our first step here? Right, it should be Friedel-Crafts acylation. Aluminum chloride, acetyl chloride will form the acetophenone. And then what? Second step, we need to do bromination. Okay, ferric bromide and bromine. And that is a meta-director, and that will give us that. What if we flip the order here, right? So if we flip the order, right, we're not going to get the meta product. If we flip the order here, we would get the para product, or maybe ortho, or maybe a mix there. So if we did bromination first and then acylation, you see, 1, 2, we'd get the wrong stereochemistry, okay? But if we do it in this order, Friedel-Crafts acylation first and then bromination. Look, then we get the correct one. But that changes the products, okay? So when we give you a product that you're shooting for, make sure you carefully examine the selectivity and how that might work, okay? How about this one? Let's do this. Let's see, what product do we want you to form now? How about an ethyl group and a chloride? Okay. So which are we going to put on first? And you can notice here they're actually reinforcing each other, right? This is an ortho-para director, and this is also ortho-para director. But what one is best to put on first? Let's see. Friedel-Crafts doesn't like to be done on deactivated rings. And yeah, this isn't strongly deactivating, but that would make that reaction very slow. So the first one that should go on here, this is one where if you mix up the order, you'd still get full credit, I think. So let's see. I don't know. Should we still give them full credit if they mix up the order on this? Yeah, Aaron says you're okay on mixing up the order. I always like to check, though. Okay. So if we alkylate first and then chlorinate, you see we can get a good reaction. Why? Because we put on the ethyl group, which is a donor, okay? And then it's going to make this step quicker. Whereas if we put on the chloride first, yeah, we could still do alkylation, but it'd be a little bit slower. But there's one where the order doesn't really matter. But let's say we want this one. By the way, here, this second step here, you would get some of the ortho also. And so if you were asked to supply the ortho product, you could do the same sequence and just say separate. But the meta product is different. How are we going to get that? Let's see. Again, this is ortho-para directing. This is also ortho-para. So these are not enforcing each other at all, even if we put on either one first. So what can we do here? What's the solution here? Yeah, so we first do acylation. Now, why do I say that? That's not the product. We don't need this aromatic ketone. We don't need acetophenone. Why am I putting that on first? Because this is what? This is indeed a meta-director. Okay, so we can put that on. And then can we change that aromatic ketone to just the alkyl? Yeah. Remember from last time, what are those two conditions we gave you? Clemenson, right, with HCl, zinc amalgam, or Wolff-Kishner, right, with the base and the hydrazine reagent. But let's see, so our next step needs to be what? Chlorination. And we'll get this. That's still not the product, right? But it enforces it as a meta-director, right? This carbonyl is conjugated to benzene ring. So this we want to put on the next electrophile such that the plus charge of the intermediate is never right next door to the withdrawing group. Okay, does that make sense? Yep, and then we got that. And then what? It's Clemenson or Wolff-Kishner. And remind yourself of what those reagents are. That reduces the aromatic ketone and puts the hydrogens there. You don't need to know the mechanism. They are known. You can look them up or I can show you, but I've never put them on a quiz or a test. It's not in your book, so there we're letting you off the hook. You don't need to know the mechanism of these two, but you need to know the reactivity and how to use them in multi-step applications. And this is certainly one where you have to, because you need the meta-directing effect of the aromatic ketone in this case, and then you can easily reduce it off, okay? Questions on that? Yeah, so this is good. You can then, imagine putting on a third or even a fourth group here, right? And then unmasking that if you need to. So you've got some flexibility here with how you can approach that problem. So the meta one's available there, and we can do that efficiently there. Let's look at synthesis here of a molecule we've talked about already. And this is PABA. PABA, para-amino benzoic acid. And what does it look like? It's got carboxylic acid here and an amino group, an aniline group. Now, how can we make that from benzene? Do you know all the steps? And have we covered that? Let's see. What do we need to do to form PABA? Well, we need to put on first a methyl group. So how about methyl iodide and aluminum chloride? And that will give us what? Toluene. Wow, toluene's not in PABA. Why are we putting on a methyl group? Well, it's a good ortho-para director. And yeah, we're going to put on another group that's not part of the final product. We're going to nitrate that. We've already done that, right? These two steps are already known for us, right? We get some ortho also, we can separate that. Now, how do we convert an alkyl group into a carboxylic acid? If you remember that, that's with chromic acid, H2Cr for chromium 04. Now, there are different ways to form chromic acid in a reaction. You can form it from the sodium or potassium dichromate salt and sulfuric acid. It doesn't matter. But if you've got the acidic form here with chromate, okay, chromium, this is a transition metal. Don't confuse this with sulfuric acid with a sulfur there. This is chromium. And don't confuse it with carbonate. If you don't look at the R here, that'd be the carbon acid, right? But here we've got chromate, okay, for chromic acid. And what does that do? That converts any alkyl group, and we'll have to talk about maybe an exception to that. You can't have a tertiary alkyl group here. So tert-butyl there gives no reaction. But any other type of alkyl, including a long chain there, and that will actually break carbon-carbon bonds. Again, you don't need to know the mechanism, but you need to know how to take any type of alkyl group and oxidize it to the carboxylic acid. The nitro group's still there. It's in oxidized form already, so it just goes along for the ride. But we're close there. We've got the benzoic acid part of PABA. How do we convert the nitro then into the aniline? There's two ways to do that in your book. One is with tin metal and HCl. That's probably the cheapest way to do it, okay? And historically, that's how it was often done. Again, another reaction you don't need to know the mechanism of. Water ends up, taking the oxygens off there. Tin is a redox active metal. It's in reduced state. There is an electron pushing pathway for this, but again, you don't need to know it. If you're curious, you can find it. Or what do we do here? Hydrogen and palladium. Actually, a lot of different transition metals will do this hydrogenation. Okay. And so platinum or even nickel and some others will do this. This is a very fast reaction, but the palladium's expensive. So a lot of times people prefer the tin. Again, we're giving you two choices. They're kind of like the Clemenson and Wolff-Kishner. But this will reduce the nitro group to the aniline, and it'll leave the carboxylic acid alone. Remember we said it's harder to reduce carboxylic acids that came up before. We need other reagents. We'll see that later on, how we can do that. But here's the, how many steps to make PABA? 1, 2, 3, 4 steps. Okay, so PABA is an important reagent. It's also a sunscreen blocker. It's in some of the sunscreen lotions. Maybe you're taking, look at the ingredients. Some of them have that. I think it's in the UVA range that it absorbs. You can see you got a lot of conjugation here. So it can absorb high energy light that way. It's also the precursor in bacteria to folate. And that pathway is inhibited by the sulfa drugs. We showed you that application. We showed you how to make the sulfa drugs before. But here we're showing you how to make PABA, which is kind of cool. Okay, one other extra reaction here is the benzylic halogenation. So if we've got an alkyl group on there already, and it can be a longer chain, whatever alkyl group, we can react this with bromine and light, okay, or NBS, N-bromosuccinimide, and we can use light or we can use peroxide to do this. So what type of reaction is this going to be? Right, it's a radical reaction, chapter 15 from 351. I know some of you didn't have chapter 15 with Dr. Peterson. I've caught a couple of you up on some of the reactions. All my materials for reviewing chapter 15 are on our Learning Suite page. And of course, you have that chapter in your ebook, so you can review that, whatever. But what you generate here is what? Bromine radical. Okay, so we don't have the Lewis acid in here with the bromine, so we're not putting the bromine on the ring. We're doing this benzylic bromination. So if we've got a hydrogen atom at the benzylic position, and that's what we need here, we can take that off, and our intermediate will look like this, which is a benzyl radical and HBr. Okay. This benzyl radical can resonate, and we have single fishhook arrows, and I'll draw just maybe one resonance structure, but you can see how it can resonate, can delocalize that single electron around the ring, just like we delocalize the cation. By the way, you can delocalize anions around the ring as well. Okay, so you've got this extra electron density here and this here, and we selectively take this one off. We don't take any of the hydrogens off around the ring because those are perpendicular. We don't give conjugation and resonance stability. It's only at the benzylic position that we're talking about here that gives us that. And then this reacts with more bromine or more NBS, right? A second step, and that gives us the benzyl bromide. Okay. Okay. And that's a cool reaction because it converts the methyl group into what? This is a good what? Leaving group now. And we can react this with all sorts of good nucleophiles and even poorer nucleophiles. We can do SN2 and SN1 reactions with these benzyl leaving groups. So that opens up a lot of other products here for us, combining this. One I'll show you just real quick is Friedel-Crafts alkylation. And maybe we showed this one last time. Did we show styrene synthesis? Yeah, let me remind you of that. So let's say NBS and light, okay? That will form the benzyl bromide. And then what? It's not just, you know, substitutions of different nucleophiles. If we do, what, TB-toxide now what do we get? We get styrene, yeah. And yeah, remember we said we couldn't do electrophilic aromatic substitution on sp2 halides. There are a couple factors we pointed out. But you can do this E2 thing after we put on a benzyl group. Okay, so that opens up some other possibilities that help us to do different types of reactions. Okay, let's see. And now we still got a couple minutes here before we wrap up the first hour. There is an alternative aromatic substitution pathway. And this is called nucleophilic aromatic substitution, or NAS, okay? Before we had EAS, electrophilic aromatic substitution. So what does this term imply? Yeah, we're going to use nucleophiles now, and they actually have to be pretty strong nucleophiles. And we have to have a leaving group somewhere on the benzene, okay? And we have to have resonance stabilization of the aromatic anion, okay? So there's some factors here that kind of necessitate some things. But this looks kind of funny at first because you're used to electrophilic aromatic substitution. But let's see this. So if we have this para nitrochlorobenzene, right? And let's react this with sodium hydroxide. Guess what our product is? It's the phenol. This isn't one of our 5 electrophiles, right? This is a strong, charged, small nucleophile, hydroxide, right? How does this work? Well, let's take our anion here and attack. You see where it ends up right here. Here's a good leaving group, chloride, bromide, tosylate. Those are all good leaving groups. But are we attacking here and doing a direct attack? It looks like I'm trying to do SN2 displacement on an aromatic position. No, I'm not doing SN2. I'm doing NAS. So it looks like it's SN2, but it's not. When you attack here, you can push these electrons here and over toward the nitro group. And it's good to draw out the resonance structures, the intermediates here. We've got the chloride, the OH. We've pushed that double bond over. And look, we've got the nitro group here. And we have a negative charge down here. Now, why is that a good thing? Yeah, because the nitro group's a strong electron withdrawing group. It's polarizing the electron toward itself. And you can see right here, we can draw some other resonance structures, right? I'm not going to draw them, but you can draw some more resonance structures. And you can draw another one here by putting the negative charge up there. So you see, because you have these electron deficient groups, and the leading group's an electron deficient group also, deactivating whatever. So it's attractive to a nucleophile now to come in. And then how do we get to the product here? Well, we've got to get rid of the chloride. So instead of delocalizing here, let's take these electrons back and kick off the chloride. So the electrons come in, they get stabilized, and they get kicked back out because of the leaving group, chloride minus coming off. You have to acidify this a little bit. The pKa of phenol is 10. So part of the workup of this reaction is to add a little bit of an acid there to protonate the phenol. But yeah, you see you get that substitution there. There's a problem on the quiz, I think, where I want you to draw the mechanism and the selectivity for this reaction. Let's see, dichloronitrobenzene, and we're reacting this with sodium methoxide. And there's a product here, NAS product, which is this. A methoxybenzene. That's an anisole. That's the name we know. So this is what? 2-chloro-4-nitro-anisole. Okay. Now, why did I just put the methoxy position at this para thing? And how come I didn't displace that chloride? Well, that's a consequence of the mechanism. Let's see, if we attack here, we can then push the electrons over, and then we get that extra resonance onto the nitro like we did before. But if we attack the methoxy right here and push the electrons around, the negative charge is always here, here, and here, and it's never next door to the nitro. So it's kind of like the directing effects, okay? Directing effects for NAS is where you put the nucleophile coming in that's either para or ortho to a good withdrawing group, okay? And the nitro is good withdrawing group. You don't want to come in meta to that withdrawing group, okay? But electronically, you can see that from the electron pushing. I won't do the rest of the thing, but it's similar to that mechanism I just showed you. This is the main product in high yield, 91% yield, yeah, for this guy here, for this anisole, following this, okay? Now, the NAS reaction is just kind of an extra minor reaction. The main ones, of course, are the electrophilic aromatic substitution reactions. So I think we'll leave it right here. We can stop now and take a break, but be back for part 4 and the review of sample test 1. Very good. We'll see you soon.